pull this up here. There we go. That's what you're seeing, right?
Yep.
Okay. All right. So chapter 6, we learn a lot more about functions, their behaviors, some pretty interesting things that we can do with them. In chapter 3, we learned about functions. We talked about the fact they're a very consistent mathematical rule. They take whatever number or expression you plug into them, they do some math, and then they spit out an answer. Okay? And another thing that we learned is we can take functions and we can add them, we can subtract them, multiply them, and divide them. As long as we don't produce any domain issues, we end up with another function. So if we take a look at example number 1, we've got two functions right here. So I've got the square root of x, that's f of x, and I've got 2x minus 7, that's the function we'll call g of x. And we just want to figure out what is f plus g. So we literally just take the square root of x and we add 2x minus 7. That's the function, and the notation this book uses is f plus g. They put that in parentheses, and then they write an equals there. So that's f plus g of x. If we subtract them, all we have to do is just be a little bit careful. So this is going to be the square root of x minus, and when we subtract, if there's more than one term, we definitely want to put that in parentheses. So this is going to be the square root of x minus 2x plus 7. So that's going to be f minus g of x. That's the notation that we'd use there. And then if we multiply them together, again, still pretty darn easy. It's just going to be the square root of x times 2x minus 7. And I'll forego just writing the notation there. And then if we divide them, we end up with, let's see, square root of x on the top and 2x minus 7 on the bottom. Okay, now those are all easy operations to do. We literally just do exactly what it says. Add the two functions, subtract the two functions, multiply them, divide them. But you do want to keep track of, well, what's the domain? So let's think about this. The domain for f of x. What is the domain for f of x? Greater than or equal to 0. So if I wrote it in interval notation, it's from 0 to infinity. What's the domain for g? All real. So I'm going to write that from negative infinity to infinity. So on this problem right here, once I put them together, what's the domain for this new function? It is 0 to infinity, including 0. That's what it is. It's the more restrictive of the two, okay? So this is going to be from 0 to infinity. Even though I can plug negatives into this, because I can't plug it into this one term that's part of that function, I have to use that smaller domain, that restricted domain from 0 to infinity. What is it for this second one, for f minus g? Same thing. It's going to be from 0 to infinity. Okay, what about this third one, the product of the two of them? Same thing. It's going to be from 0 to infinity. Okay, and what about this last one, f divided by g? Okay, so say that again, Christopher. Okay, we've got to throw in another one. And why do we have to throw in that other one? Okay, by virtue of the operation that we put in there, we put in a division problem there. And because g of x ends up on the bottom, we have to be careful. Yeah, you could plug anything you want in there to begin with, but now we've got to be careful because what comes out of here can't be a 0. We can't produce a 0 in the denominator. Okay? So when we start doing all of these algebraic operations with functions, you have to be pretty darn careful about domain issues. Okay, so you got to keep an eye on that. So we found each one of those, and now we're going to talk about something different. This is called a composite function. Okay, they're a little bit more complicated type of algebra that we do with functions. Okay, composite functions are created when one function gets plugged into another function. So composite functions are created when one function gets, we'll say, plugged into. I suppose the technical term for that would be substituted into, or used as an argument in another function. So if we think about how regular functions work, we're familiar with function notation like f of x and g of x and stuff like that. So if I dump in an x f does something to it, and what comes out is f of x. So here's the function f. I put in an x. What comes out is f of x. I put in an x, and what comes out is a function value, or a lot of times we'll call that a y. So if we think about a composite function, we're going to put a function into another function, okay? So we're going to plug in g of x, so we're going to dump that in here, and what comes out is f of g of x. Notice that it's in the same place as the x was before. So what we get out is f of g of x. Now, I like this notation. You may have seen composite functions before. You may have seen this type of notation, okay? So this one right here, a lot of people look at this and say, oh, that's fog. Okay, that little symbol, it's not a 0, it's not an O. Okay, it means a composite of those two functions. Okay, you could write g of f of x like this. Okay, I like this a lot better. Both of these are said the same way. So if I see this, I say f of g of x. If I see this, I say f of g of x. They both mean the same thing. They're just different types of notation. I like to focus on this one right here. This is the one that we'll use most often. Okay? The reason I like this is you can look at this and you can tell what happened here. What got plugged into what? G got plugged into F. Okay? Sometimes we'll call this the outside, and that is the inside. Okay? So G got plugged into F, so G's the inside, F is the outside. Okay? That type of thinking can come in handy in the long run. Okay, are there any questions there? Okay, so now we're going to take the same two functions and we're going to look at how we can think of them as a composite. So I can write a new function, h of x, as a composite of these two functions right here. So I've got h is the square root of 2x minus 7. It's a composite of the square root function and 2x minus 7. What got plugged into what here? Say that again? Okay, so this is f of g of x. That's what h of x is. And the reason is, if I take the function f, it's a square root. What are we going to plug into that? We're going to plug g of x. What's g of x? 2x minus 7. So there's the composite. It's a composite of f of g of x. Now, just for the heck of it, I'm going to change colors here. Let's say I made a new function. Let's call this, let's call it j of x. And let's have that be g of f of x. Let's compose these the other way. What got plugged into what here? F got plugged into g. So g is the function 2 times something minus 7. What are we plugging into g? The square root of x. So if I simplified that, it would be 2 radical x minus 7. So this is g of f of x. This is f of g of x. Okay? So the order you compose these makes a huge difference in the end result. Okay? All right. Any questions there? Okay, raise your hand if you've seen composite functions before. Excellent. Let's keep going then, okay, because it's going to get a little bit more interesting. So on this problem right here, it says if f is 2 over x minus 3 and g of x is x squared minus 1, what is f of g of 4? So again, it's that other type of notation. If you want to write it like this, this would be f of g of 4. So this is what we do. We start at the very inside. I'm going to take 4, and what am I going to plug it into? I'm going to plug it into g. So I'm going to take 4, I'll plug it into g. What comes out? If I plug 4 into g, I get 15. I'm going to take that, what am I going to plug it into? I'm going to plug it into f. So if I plug it into f, and on this one I'll literally just plug this in, this is 2 over 15 minus 3. So this is 2 over 12. So the answer is 1/6. There's our answer. That would be f of g of 4. And again, what we did right here is we did 4 squared minus 1 to get the 15. So you're taking a number or an expression, plugging it into one function, getting an answer, and then plugging that into another one. And if you think about it, there's no reason we couldn't make a composite function of three functions. Plug it into one, get an answer, take that answer, plug it into another, take that answer, plug it into another. This could go on and on and on, okay? It won't. We usually just do two, but you could do more than that. Okay, let's take a look at the next one. We want to figure out what g of f of 2 is. Again, if you need to, write it this way, g of f of 2. We start with a 2. What do we plug it into? Plug it into f. So if I take 2 and plug it into f, f of 2 is? Yep, plug in a 2, I get 2 over 2 minus 3, that's going to be a negative 1, so we get a negative 2. I'm then going to take that and I'm going to plug it into the g. So if I plug a negative 2 into g, I get negative 2 squared, which is 4 minus 1, so the answer is 3. So g of f of 2 is positive 3. Any questions? Okay, what does this mean we do? Could somebody describe this? Tylin, how about you? What are we doing here? F of 4. Not really. We don't times them. Yeah.
So you plug 4 into the first f, and then you plug that answer into the f again.
Yep. So we're going to take 4 and we're going to plug it in here. So we're going to do 2 over 4 minus 3. So that's going to be a 1, right? So what I get out is a 2. I'm then going to take that and I'm going to plug it right back in. So this was f of, this was f of 4. Now I'm going to take this and I'm going to figure out what f of 2 is. So if I plug a 2, I'm going to take it and plug it right back into the same function it came from. So that's going to be 2 over 2 minus 3. That's going to be 2 over negative 1. So my answer is negative 2. There's my answer on that one. Does that make sense? This means take 4, plug it into f, take that answer, plug it right back into f. And this one, of course, means take 2, plug it into g, take that answer, plug it into f. Would you go ahead and find the solution to that one there? So this is f of g of 2. I see some raised eyebrows. That's good, because here's what happens. I take 2, I plug it into g, and what do I get out? Yeah, I get 2 squared is 4 minus 1, so I end up with a 3. I'm supposed to plug that into f, right? So if I plug that into f, here's what I'm supposed to do. I'm going to find f of 3, which means I'm on this one right here, 2 over 3 minus 3, and what happens? So this is undefined, does not exist, something like that. It does not exist because 2 is not in the domain of that composite function. If I were to figure out what this composite function is, I can't plug in a 2 because I don't get an answer. It's not in the domain. And we're going to talk about why it's not in the domain a little bit later. Okay, now you do have a couple problems, and this is actually a good thing because in pre-calculus we spend a lot of time looking at graphs and figuring out what function values are. This is a part where we can stretch our brains just a little bit that will help us in the long run in calculus because we look at a lot of graphs in calculus. So on this, there's not really any work to do, but there's a lot of thinking that goes on here. So we're going to take a look at this first one right here. We want to figure out what g of f of negative 1 is. So this whole idea of, this one right here, take 4, plug it into f, take that, plug it right back into f. Let it be the new x value, so to speak. So here's what we do on this one. What do we start with? We start with negative 1. Okay, so let's take a look at this graph. If I start with negative 1, I'm right here. I want to figure out f of negative 1. So here's negative 1. This is g. The curly thing is g. That line right here, that piecewise function, kind of looks like an absolute value graph. That's f. Okay? So G's here and F is here. So what function value do I want? Do I want the 3 or the 1? I want the 1. Okay, now listen carefully. Once I figure out the function value here, what I'm doing now is I'm figuring out, well, what is G of 1? Okay, watch. My old Y value becomes my new X value. So I'm going to go to 1. And do I want G or do I want F of 1? I want G. So what's my answer? My answer is 4. Okay? So G of F of negative 1 becomes G of 1. In other words, I take the 1 that I got out of F, I plug it back into G. You with me there? Okay, let's do this one. I start with 0. 0's right here. I plug that into F. So do I want this one up here at 5 or do I want the 0? I want the 0. Okay? So this becomes G of 0. And what is G of 0? G of 0 is 5. So there's my answer on that one. There's no work to write down. You can't figure this out. I mean, I suppose you could write this, and maybe that helps a little bit. But this is just thinking. What I'm doing is I'm plugging an X in, I'm getting a function value out, and then I'm plugging that into another function, or in other words, I'm taking the old Y and making it the X that I plug into the new function. Does that make sense? So let's take a look at the next one. This is F of G of negative 1. It's similar to the one we did up here, but here's negative 1. I want G of negative 1. What is that? Okay, so I'm going to follow that up. That's a 3. My function value of 3 now needs to get plugged into X. So this is my new X value. So I'm going to follow that over here. And what is the X value right here on, or excuse me, the Y value, the function value on F? Negative 1. So the answer here is negative 1. Okay? Do I need to do another one, or do you get the idea? Okay? Do we need to do them both? I'll do them both if you want. If you want to see them both, just pop your hand up if you want to see them both. Okay, let's do them both. Okay, what do I start with? Start with 4. Okay, I'm going to change colors here. So I start with 4. 4 is right here. If I want F of G of 4, am I staying on F and finding the function value there, or am I going up on G? Going up on G. What's the function value right here? It's 2, right? So this becomes F of 2. So I go to 2. The function F is this line thing right here. So I go to 2. What's my function value there? Answer here is negative 2. This is worth times. I mean, it's not like your entire assignment is like this. Most of it's algebraic. But being able to look at a graph and figure stuff like this out is a very important skill to develop, because you do stuff that's similar to this in calculus. Not the same, but similar. You build on that idea right there. So let's take a look at the last one. The last one is G of F of 2. So I start off at 2. So here's 2. I find F of 2. F of 2 is negative 2. So I'm trying to find what is G of negative 2. So I come over here to negative 2. Is there a value? Nope, not on G. G stops right there. So this does not exist. It was okay to plug a 2 into F, but what came out of there doesn't exist as far as values on G. Yeah. Oh, does not exist. I thought we'd used that before. Have we not? No? Okay. So DNE means does not exist. You could write no solution. Okay? Something like that. Thanks for pointing that out. Yeah.
For the no solution, can you just write a 0 with a line across?
That's okay. So technically, if you're going to write that, it should be in set bracket notation, because this is technically called the empty set. Okay? And that's the notation for the empty set. Okay? There are countries where that literally means 0, means the number 0. So you want to be a little bit careful with that. Okay. Any questions? We got that idea figured out? Okay, you've got a few where there are graphs. Let's take a look at the next part. So on the back side, here's what we've got. We've got problems similar and functions similar to what we saw on the front side, only this time the instructions changed just a little bit. So it says if f of x is the square root of x and g of x is 3x minus 5, find f of g of x, which hopefully shouldn't be too terribly difficult, and state its domain. And state its domain. So here's what we want to do. We want to find f of g of x. So what gets plugged into what here? G's the inside, it gets plugged into the outside function f. So this is the square root of, and what are we going to plug in? 3x minus 5. Okay, now, if you think about the original function, this has a domain from 0 to infinity. This has a domain from negative infinity to infinity. Now, think very carefully here. This is not as simple as saying, well, gosh, I'm just going to take this and take the smaller of the two. It doesn't work that way, okay? Composite functions are algebraically much more complicated than adding, subtracting, multiplying, and dividing. You're literally taking one function and plugging into another function to make a completely new one, okay? So here's generally the best thing to do, and I've got it outlined over here, okay? Assume the domain is all real numbers. So assume you've got everything you need to start with. Throw out anything that's not in the domain of the inside function. So if we look at the inside function here, g, it's still negative infinity to infinity, okay? Find the composite function and then throw out anything that you need to in the end. So once you've simplified this, let's take a look at this. This is a square root function. You can't plug anything you want into a square root function. You have to make sure that this right here is greater than or equal to 0. So let's solve that inequality. That would be 3x greater than or equal to 5. Divide by 3. I don't need to worry about changing directions of the inequality. This would be x greater than or equal to 5/3. If I wanted to write that in set builder notation, you remember that from Math 1010? You could write it that way. I'd much prefer you write this in interval notation, so please write it in interval notation. This means all of the x's that are bigger than or equal to 5/3. So 5/3 is here, and we'd go this way. So that's going to be from positive 5/3 all the way to infinity with a square bracket there. Okay? So this is the composite function. This is the domain. It's a lot smaller than what we started out with. Any questions there? Okay, let's take a look at the next one. Okay, these get a little bit interesting, and it's important. The technique I just showed you, assume it's all real numbers, throw out anything you need to throw out with the inside function, and then simplify it and throw out anything in the end. That'll work every single time, but it's important to think about why what we have to throw out in the end doesn't work, okay? So let's just keep track of this verbally. What can't you plug into this? A -3, right? I'm going to write that up here, just a -3 there. What can't I plug into this? A 0. Now, what do I start with? What gets plugged into what here? G gets plugged into F. So what do I definitely need to throw out to begin with? Okay, I can't have it equal 0. I'm going to throw that out. Okay, I know that's not in the domain because I can't even start by plugging in a 0. You with me there? Okay, now I'm going to figure out what f of g of x is. I'm literally going to plug in g into f. So wherever there used to be an x, what am I plugging in for it? A -2 over x. You with me? Okay, then we want to go through and we want to simplify. We certainly don't want to work with it like this. So if you know the rules for simplifying a complex fraction, we went over 2 methods. I'm going to do it using this method. I'm going to get a common denominator on the bottom. So this now becomes 1 over -2 over x plus 3x over x. which what that allows me to do, it allows me to combine these. So this is going to be 3x minus 2 over x. You with me there? Any questions? Okay. Then I'm going to take the bottom and I'm going to flip it over and I'm going to multiply by it. So I'm going to multiply by x over 3x minus 2. You okay there? So here's the final answer. This is the simplified form. This is f of g of x. This is about as nice as you can make it. There's an x on the top and there's a 3x minus 2 on the bottom. Okay, are there any questions about that? Because you have several problems that deal with rational functions. Okay. The domain for this, what did we say you already have to throw out? What did we say there's no way you can use it? 0. Okay. Now, take a look at this end result. What else do we need to throw out? Okay, we need to throw out what would make the denominator 0. So that's going to be 2/3. Okay. And this would be the answer to that particular problem. Okay. There's the composite function. There's its domain. Yes.
So I might just guess that, but not sure. How come we don't throw out -3 on one of them?
That's what we're going to look at right now. Okay. If you can figure this out, then I'm really impressed with your thinking skills to this point. Okay, there are a couple of questions. Why don't we throw out -3? That's the first question. And then the other question is, well, wait a minute. Take a good look at this. I can plug 0 in there. Can't I? If I plugged a 0 in, I'd get a 0 on the top and I'd get a -2 on the bottom. The answer would be 0. There wouldn't be anything wrong with that. And yet we still have to throw it out. So we've got 2 questions to deal with. That last question is the easiest. Okay, why do we still have to throw out 0? That's number 1. And the second question is, why don't we have to throw out -3? Okay, so let's deal with the first question. Do you know one of the answers?
Well, I just think it's from whenever you start, whatever it's asking from to your answer, anything you get in between there, that's part of the domain. The reason why you don't do -3 is because that's not part of the first question.
Excellent. Okay, that's not where we start. Okay, so let's deal with the easy question first. Why do we still have to throw out 0? Because this is the simplified version. Look right here. This is literally what you get when you plug in g into f. If I plugged in a 0, wouldn't that make this piece undefined? Yes, it would. So we still need to keep 0 out of our domain. Now let's deal with the 3. Here's the interesting part. Watch what happens if I plug in a 2/3 into this. So if I find g of 2/3, that's a -2 over 2/3. I'd flip this over. This would be 3 over 2. What do I get out? A -3. Now, what would I be trying to do? I'd be trying to take what comes out of g and I'd be trying to plug it in right here. Does that work? It doesn't. Okay? So you have to make sure that what comes out of the first one is okay to plug into the second one. What's not okay to plug into the second one? -3, so you better not plug in a 2/3 into this one because that produces the -3 that Zach was worried about. Does that make sense? That is a very complex idea. Think about it for a minute. Try and make it have it make sense. Yeah.
So if we were going to reverse it, if it was g of x or g of f of x, would we throw out -3, but we wouldn't throw out 0?
Yeah. Can you tell me why? So if you're not worried, if you don't get this, don't worry about it. Can you tell me why?
Just because, like, if we throw out -3, if we plug that, I think. So once we get down to the simplified version, we would pretty much be plugging -3, which would cause that to be 0 to plug into the next one.
Okay, here's why. Here's one way to think of it. Okay, we're going to take, so Zach's saying, what if we did g of f of x? Okay, we'd have to throw out -3 to start with, right? That's gone. Okay, what can't we plug into this? A 0. Does this ever equal 0? It never does. So the only thing we'd have to throw out on that one is just the -3. Does that make sense? Think about it for a while. Okay? All right, any questions? Okay, let's take a look at the next couple. Okay, this is problem number 36, and you have several problems on your assignment that have multiple parts. Okay, now what would be really nice is if we could figure these out relatively quickly. Now, I think I did you a favor. Do you notice anything about 22 and 36?
It's the same equation.
Okay, part of it is the same. This one says f of g of x, so we've taken care of this one right here. So f of g of x, and I'm going to write it using this notation because I like that a lot better. You can literally see what's getting plugged into what. It's x over 3x minus 2, and the domain is x not equal to 0 or 2/3. Okay? So that part's done for us. Let's take a look at this one, and this is what Zach was concerned about. What if we switched these? Let's figure out what g of f of x is. So I'm literally going to take f of x and I'm going to put it into g. You with me? So that's going to be negative 2 over, 1 over x plus 3. Now, it said you've always got to throw out whatever you're starting with. What do I need to throw out here? I need to throw out a negative 3. Let's do some simplification. Holy cow, look at this. Look how nice this is. All I have to do is flip the bottom over and multiply. The denominator would be 1, and I'd end up with this, negative 2 times x plus 3. Are there any domain issues that I've introduced here? Do I have to throw anything else out? No, I don't. I don't. Okay, so here's the domain. X not equal to negative 3. There's the function. Now, on this one, if you wanted to distribute through, that would be totally fine with me. Oh, come on. Yeah, question?
So you said we flip the bottom 1 to the top so that negative 2 can multiply by x plus 3, right?
Mm-hmm.
How do we, that doesn't make sense to me. Like, why?
If I did 3/4 divided by 1/2, how would you do that problem?
I use my calculator.
Okay, okay.
Yes.
Honest answer, but not what we're looking for.
I know.
We never divide fractions. We always flip the second one over, so we'd multiply by 2 over 1. Okay, and then we'd simplify from there. So most people would write down 6/4. It would be a heck of a lot better if we cross-canceled and stuff like that. But we've got this number divided by that fraction, so I flip that fraction over and I multiply. Okay. If you have more questions, come see me after. We'll play around with some complex fractions. Okay. F of f. F of f. What do I throw out to begin with? Got to throw out the negative 3. Okay. Now f of f looks like this. I'm going to take 1 over. What am I plugging in here? Which is 1 over x plus 3 plus 3, right? Okay, so on that ugly mess, I do have some simplification to do. So let's clean this up just a little bit. I'm going to get a common denominator of x plus 3. So let's see, this is going to be 1 over x plus 3 plus 3x plus 9 over x plus 3. So this is 1 over, help me out here, isn't that 3x plus 10 over x plus 3? And then I'm going to flip this over and multiply. So that's going to be x plus 3 over 3x plus 10. If I multiply by 1, that doesn't change it at all. So f, oops, let me change back. So we're in blue. f of x is equal to x plus 3 over 3x plus 10. We already said you had to throw out negative 3. What else do you have to throw out? You have to throw out negative 10/3. You might, it would, in my opinion, it would be worth your time to try and figure out why you have to throw out negative 10/3, even though that doesn't have anything to do with the domain of the original function. Okay? And g of g is actually pretty easy. So let's take a look at that. It's negative 2 over x. So if I find g of x, it's negative 2 over x. Now, what am I throwing out to begin with? I'm throwing out a 0. Tylin, what do we get when we simplify this? We do get something that's actually not a number. If I take this and I flip it over and I multiply, the 2's would cancel and I'd end up with x. So this is a little bit of an interesting problem, and we're going to talk about this over the next couple of days. If I plug this function into itself, I get x. I started with x, I did some math to it, I did some more math to it, and I got right back to x. Okay? I still have to throw out 0. Do I have to throw out anything else? You don't, and just like that negative 3/10, it's worth your time figuring out why I don't have to throw out anything else. Okay? All right. Kind of. You might want to think about what values come out of this and where we're trying to plug them in. Okay. So here's the last little bit, and this is what I was alluding to. It says, what relationship do x cubed and the cube root of x have? What's the word, Justin?
Reciprocals.
Not reciprocals. They're inverses. Okay? They are inverses. Okay? Now, we kind of use the word reciprocal for that sometimes, but that's technically not correct. So the notation that we use here is f, and this is f inverse. This is not f to the negative 1. Please don't confuse that. It's not an exponent. Okay? If you write a negative 1, superscript is what we call it. Kind of looks like an exponent. If you write that over a function, it means the inverse of that function. Okay? If they're inverses, and I think I taught in my 10-10 class this, if they're inverses, what should they do to each other?
Cancel.
Okay, cancel is one word, or a better word is undo. They should undo each other. Okay? So if they truly are inverses, whatever one did, the other one should undo. So if I do f of f inverse, if this does some math and this does the opposite math, if they undo each other, I should get right back to x. So if I plug in x, do some math to it, and then undo that math, I should get right back where I started. Or in other words, if I plug x into f, what comes out is f of x. If this undoes that, so even if it's in the opposite order, I should end up with plain old x. So let me write one more thing. This one does something. This one undoes that thing, and we get right back where we started. So we're going to take a look at a fairly simple example, nice easy function like cube root and cubing. If I were to take this function and plug it into that one, or vice versa. So let's say I found f of f inverse. So that would be, take something and cube it. What am I plugging into the cubing function? The cube root. What do these two do to each other? They undo each other, so what's the answer? The answer is x. So I plugged x into f inverse, and then I undid that. I get right back to x. Let's look at this one. This is composed the other way. This is f inverse of f. So the way I've got this written is f inverse is the cube root function. And what am I plugging into the cube root function? X cubed. What do they do to each other? They undo each other, so I get just a plain old x. Okay, so on this particular assignment, all they ask you to do are things like this. It says, given f of x is 2x minus 6, and g of x is 1/2 x plus 6 in parentheses, show that f of g of x and g of f of x are both x. Show that they undo each other. Show that they're actually inverses. So let's do f of g of x. That means 2 times something minus 6. What is that something I'm plugging in? I'm doing f of g of x, so I'm plugging g into f. So this is the 1/2 x plus 6. What's 2 times a half? 1. So this is 1 times x plus 6 minus 6. What's 6 minus 6? 0. So I get x plus 0, which is x. Did it equal x? Do they undo each other? You bet they did, so they must be inverses. Now we want to do it the opposite way. G of f of x. So would you write that down, please? Write what you'd plug into what? Don't simplify anything, just literally plug f into g. So g is 1/2 of something plus 6. There's g, 1/2 of something plus 6. What am I plugging in? I'm plugging in f, which is 2x minus 6. So let's use PEMDAS. Please excuse my dear Aunt Sally, the order of operations. I do the stuff inside parentheses first. This would be 1/2 of 2x minus 6 plus 6. That's going to be 1/2 of 2x, and 1/2 of 2x is x. Got it? Okay. So that's a bunch of composite functions. That's how they work. That's how we compose them. That's how we figure out what their domain is and all that sort of stuff. Now we've got one more type of problem to take a look at, and it's number 53. And it says this, and for some reason, it depends on who you are. If you get these and these just happen to click, this is a piece of cake. If not, you can sit and stare at this and go, I don't have any idea what to do, okay? Because this is not an algebra question. This is an understanding question. Do you get what composite functions do? Do you get that it's one function plugged into another? So it says, find functions f and g so that f of g is h. So that when you take f of g of x, you get h of x. You get that function right there. And again, this is where it's useful to think in terms of what's the inside function? What got plugged into the outside function? So f of x, we'll call that the outside. And g of x, we'll call that the inside. Now, I'm hoping that after everything we've gone through, I'm hoping that that's enough that everybody knows what these are. What's the outside function? It's x. X to the fourth. What's the inside function? 2x plus 3. Very good. Okay? So that would work right there. Now, outside, inside, that's my terminology, but I think it's really good. If you take calculus, we actually use those words. Let me show you one more thing. You don't have to write this down. I want you to watch. Would that work? Would f of g of x still be that same h of x? It would, wouldn't it? Okay, that's a weird way to do it. But if I took this and plugged it in right there, wherever there was an x in f of x, I'd still get 2x plus 3 quantity to the fourth. Yeah.
You wrote g of x equals 2x plus 4, it's 2x plus 3.
Oh, is it plus? Oh, thanks. Thanks.
We all understood what you said.
Well, that's good you understood that. Okay. Anything else? Okay. If you've got a question about your test, please see me. Otherwise, great job there. And get started on the homework. Stay on top of stuff, and we'll see you tomorrow. And if you weren't here at the beginning, come up and I'll show you your test.